Hi, this is Miss Logan. Today we'll be moving on to periodic and harmonic motion. Today's flipped lesson, I'm going to go over basic vocabulary that's really going to root this chapter and help us be successful in our pendulum lab. We can define periodic motion as any time a motion repeats itself. So a very common example of this is a grandfather's clock, and this pendulum in the middle is moving back and forth at a constant rate. Other examples are when we have an object that is moving along a track at a constant velocity back and forth forever and ever. A fun example could be a dog wagging its tail. So when dogs are wagging their tail, they're wagging them back and forth with constant motion. One of the most important vocabulary words to periodic motion is period, which we use the capital T. So this is the time it takes to complete one cycle. And by a cycle, we mean that's the start to the finish. So we're going back and we're going forth. Our units are in seconds per cycle or just in seconds. The second word that's pretty important to us is a frequency. So this is the number of oscillations or periods over units of time. So this is 1 over our period. So it's really important in this chapter, like previous chapters, that instead of just saying the abbreviation, we're actually saying the word. The units we're going to use is cycles per second or 1 over S. We also use the abbreviation HZ, which is hertz, for frequency. So simple harmonic motion is a specific type of periodic motion. And this is when a mass on a spring is oscillating. Oscillating, we just mean is going back and forth. So in this example, this spring is going back and forth at a constant motion. If we were to actually draw what was going on, we would actually get a sine graph moving back and forth. Right here, we would have our lowest point, so when the spring is most compressed, and here we would have the highest point, where our spring is the most stretched out. So just to note, this A right here is for amplitude, and amplitude is basically how high that sine graph goes. Okay, so let's talk a little bit about how we can actually get some mathematical equations to help us describe simple harmonic motion. Like on the previous slide, we're talking about something oscillating on a spring back and forth. The distance traveled is represented by this graph, which has time on the x and height or distance on the y-axis. So remember x here, we're talking about that this is the distance, and this is equal to a cosine theta. So we get that when we talk about cosine and sine graphs. A is standing for the amplitude or how high the graph goes. Now for theta, in these graphs we don't have any theta. So we need to go back to last unit where we had angular velocity is equal to theta, the distance traveled, over time. Now if we solve for theta, we're going to get theta equals angular velocity times time. We can actually plug that in right here. Now, we have to kind of connect these two chapters. In our previous chapter, we used angular velocity, but in this chapter, we can't. We need to instead go back to our vocabulary that we just talked about, period and frequency. So, let's go down here. So our angular velocity is equal to 2 pi frequency. So if we think about a circle, we're going around 2 pi in whatever frequency or rate that is for that situation. Now we can replace this frequency with 1 over t. So now we can actually plug in, instead of having this angular velocity, we can plug in our equation for angular velocity anytime that we have simple harmonic motion. So this equation is probably one of the most important equations that we're going to see this chapter. We're really relating rotational motion to our simple harmonic motion. Okay, so let's go a little bit further with this. Now, we know all the way back from last unit, we have force is equal to force spring. So this is force total is equal to force spring. So another way we can write this force is mass times acceleration. And we can write force in a spring negative kx, where k is our spring constant and x is the distance traveled. So from here we can plug in some different numbers. So for A, we can plug in this pretty big equation. So we have negative A, which is our amplitude, times angular velocity squared, cosine angular velocity times time. So where are we getting this? We are getting this from our cosine graph equations. So going back to trig and calculus. On the other side, we have negative k, we'll keep that there. And then from the previous slide, we have a cosine angular velocity times time. That's giving us this x. Now from here, we can actually cross a lot of things out. So we can get rid of the negatives, we can get rid of the amplitude, and we can get rid of the cosine angular velocity times time. So all we're left with is angular velocity squared equal to k over m, and all we did was move this over to the other side. So another way to write our angular velocity for simple harmonic motion is the square root of k, which is our spring constant, over the mass of that object moving back and forth. So that's our second important equation that we'll be using in simple harmonic motion. Okay, so let's actually combine our two equations that have angular velocity. Because like I said before, we're really taking this time to go through these derivations so we can get rid of this angular velocity. So let's actually combine these two and set them equal to each other. Now, like I said at the beginning, t, or the period, is one of the most important factors in harmonic motion. So let's solve for it. So let's multiply both sides by t. So then I'm going to get 2 pi equals square root k over m times t. Now to solve for t, I can multiply by the reciprocal. So therefore, we have our period is equal to 2 pi square root of m over k. This is our third most important equation that we are talking about. So what does this actually mean? If I increase the mass by a factor of 4, I'm going to increase the period, or how long this sine graph is. On the other side, if I increase the amplitude by a factor of 2, if we look at these two different graphs, the period is the same. The only thing that's changed is the amplitude. Why? There's no amplitude in this entire equation. We'll see in next chapter when we talk about waves how this actually works, but it's important to note right now with our equations. If we increase our force constant, okay, by a factor of 4, we'll actually make the period shorter. We're taking the square root and k is in the denominator. If we increase the force constant of k and the mass by a factor of 4, it will stay the same. So we're going to see through our pendulum lab how these things are related. So please make sure you read sections 13.1, 13.2, and 13.4 just to get a little bit more background on this. I went through the derivations for our equations, and these are the equations that are going to help guide us through this chapter.